computational problem related to synchronizing automata. Synchronizing automata is quite simple and natural notion. Let we have a deterministic finite automaton without initial and final states. That is, it's a triple Q sigma delta, where Q is a state set, sigma is a alphabet, usually fixed alphabet of fixed size, and delta is the transition function, well-defined transition function. Then the main definition in this theory is the definition of reset what. What V is reset for an automaton A if it takes the automaton in one particular state, no matter of the original one. And it can be written in several equivalent forms. For instance, that delta of QV is equal to delta of PV for all states QP, or the cardinality of the image of the full set of states under the action of this what is equal to 1. And if an automaton possesses at least one reset what, this automaton is called synchronizing. And actually, synchronizing automata has many applications, because one can think about automaton as a model of a discrete reactive system, and then the reset what allows to reestablish the control under the corresponding system after an error has occurred there. So the main object to study in this theory is so-called reset threshold of an automaton. This is the minimum length of reset words. And below, for simplicity, we assume that P is not equal to NP, and effective means polynomial. So let's consider the simple example. We synchronize this automaton by so-called greedy algorithm. This is for state automaton with two letters A and B. Letter A only permutes states by the long cycle, and letter B leaves all states on their places, except state 4, which it moves it into state 1. And what means greedy algorithm? We start from the full set of states and try to find shortest word which merges some pair, any pair of states. It's clear that the first such word is just letter B, because letter A only permutes our states. So it makes no sense to apply letter B again, because it leaves all states on their places. So we apply letter A. It again makes no sense to apply letter B, because it becomes back to the previous position. So we apply letter A, and now we can apply letter B and apply it, because it merges states 4 and 1. And it's easy to verify that the third word will be A, B, A, B. Thus we get one state in the image. Hence, this word is reset word. Its length is 10, but actually there is more short reset word of length 9. That is, this algorithm for this automaton doesn't provide an optimal solution. So, what's the first problem? The first problem is just to return some reset word or check that automaton is synchronizing. And the question is how complicated to find such some reset word. It's clear that greedy algorithm is cubic, and it actually can be optimized to quadratic algorithm to only check that automaton is synchronizing. But nevertheless, it's effective algorithm. We have an effective algorithm. There are some open questions which can be interesting. The first one is generic complexity and some linear algorithms for subclasses of automata, algorithms for generalization of deterministic finite automata, and the last one is probability of being synchronizable. So now,
what do you mean by probability of being
synchronizable? That is, we take a random automaton, and what's the probability? This question is related with the first one, I think. There is my work in progress. It's still very raw. So we have an effective algorithm for check that automaton is synchronizing. The next natural question is, can we find the optimal value in polynomial time? Or the decision problem of this variant of this problem is as follows. Given an automaton, a synchronizing automaton, and a number k, we have to check that rest threshold is at most k. That is, there is a word of length at most k. And it has been proved in 1990 by Epstein that this problem is NP-complete, and actually his proof also implies that this co-NP hard, this problem is co-NP hard, and thus unless NP equals co-NP, there is no even non-deterministic polynomial time algorithm for this problem. However, one can ask about approximation algorithm. And let's recall the definition of approximation algorithm. Let us say that algorithm M approximates reset threshold within performance ratio f of n if the following inequality holds true. That is, it always returns the value more than the value of reset threshold and less at most f of n times reset threshold of a. And this question, the question about existence of such effective algorithm has been raised in 2008 by Volkov, and the answer has been found by myself and Gavrichowski independently in 2008 for factor less than 2 for automata with 2 input letters, which is quite important. And actually, in my result was stronger. I have shown that there is no effective approximation algorithm of reset threshold within any constant factor. But this result doesn't close the problem because one can ask about logarithmic approximation. And in 2011, Gerbusch and Heringa has proved partial result in this direction. Namely, they proved that for any constant less than some specific constant, there is no effective approximation algorithm within performance ratio, within logarithmic performance ratio with this constant. But the alphabet size in the result grows together with the number of states. And for automata, the main cases when the size of automata, the size of alphabet size is fixed, has fixed size. Especially the main interesting case is the case of binary alphabet. So
why is the binary alphabet
it's because the main theoretic problem in this theory is Cherny conjecture, and it's not proved for two-letter alphabet case. And usually it's fixed alphabets assumed to be fixed size. It has to be fixed size. So the main question is, does this result remains true for some probably other constant for any fixed non-singleton alphabet? And to solve this problem, we analyzed the proof of Gerbusch and Heringa and some another paper, another result. Gerbusch and Heringa, to prove their result, used the reduction to set cover problem. Actually, they used yes, the reduction to set cover problem. Let's recall that set cover problem is the following problem. Given a domain U and a family of sets on this domain, the problem is to find the minimal subfamily F prime that covers the domain. And this problem is reduced to find a reset threshold. And in this reduction, it's quite a transparent reduction. And number of states in the automaton is equal to the size of the domain plus 1, and the alphabet size is exactly the size of family of sets. And this is just a picture how this works. We assign to each subset a letter, and if element of is included in this set, then we map it into the 0 state, and otherwise we leave it on that place. And there is a sophisticated result of Alan, Moskovich, and Safra of 2006, where they have shown that set cover cannot be effectively approximated within performance ratio C-ln of n, where n is the size of the domain. And due to this reduction, rest-threshold also cannot be approximated within such performance ratio. And actually, there are several weaker results of the similar in this direction was before. Okay, so how using this reduction we can solve? Okay, just 2 slides, and we first construct binary automaton with binary alphabet, such that the size of the state set is equal to, that is given an automaton with alphabet sigma and state set q, we construct an automaton on binary alphabet with following properties. And the only problem is that the size of the cardinality of the state set is equal to, depends on the cardinality of the alphabet size of an original automaton. But if this, if the alphabet size is bounded by some polynomial of degree t of the number of states, then we immediately get the following, that there is no effective algorithm which approximates the threshold for automata with binary alphabet with the following performance ratio. And thus the last claim in this, last step in this proof is to analyze the reduction to the cover problem from the paper of Alan, Moskovich, and Safra to show that this t can be chosen to be arbitrarily close to 1. And thus we get the main result as a consequence that the rest threshold cannot be effectively approximated within any performance ratio d ln of n for any d less than half of c, where c is that specific constant from set cover problem, even for binary alphabet. Actually, it's clear that this result remains true for any fixed size non-singleton alphabet. So just to conclude, let's note that the set cover problem can be approximated within performance ratio of the following form, logarithmic performance ratio. And actually experiments show that the greedy algorithm also approximates rest thresholds for binary alphabet, for automata with the binary alphabet, within logarithmic performance ratio in the number of states. And thus, the main question is to get the analogous result to as for set cover problem. That is, the greedy algorithm approximates rest thresholds within performance ratio, within logarithmic performance ratio, or some another algorithm can do this. So that's all. Thank you for your attention. Any questions?
Yes, so the nature of the question is what you can improve on the approximability ratio. Can you improve at least some linear amount or something? I mean, you would like to, I mean, you told us about some approximability results.
Yes.
So what kind of approximation do you know? You can prove?
It's there is no approximation algorithm actually for. We only know that the upper bound for rest threshold is of order is cubic, but we don't know. But if we take random automata, experiments show that the rest threshold is of order square root of n. But we don't have any approximation algorithm with some. Yes, with probable. For a moment, probably we can provide now.
Any other questions?
Yeah. I think you mentioned completeness of the decision problem.
Yes.
And then you also said that there is also coin defaultness, which is
Yes.
quite strange. Or what do you mean actually?
I mean that why it's strange.
So if an NP-complete problem is in coin P,
Yes.
then it would, well, that would mean the left.
No, but maybe the length, the shortest, can be exponential. So why it's in NP?
In this,
No, the problem is in P.
I mean, if an automaton is synchronizable, then it's synchronizable with the word of polynomial length.
Yes,
So
but what's the problem?
Is in
What's
NP or not? The problem not.
it's in NP, of course.
But how can it be co-NP hard?
Yes. That's what I asked.
No, it is probably just.
Why it cannot be in coin P? Why it cannot be in coin P hard?
But if a co-NP hard, what does it mean? That you can reduce every co-NP problem to this? But this will mean that co-NP is in NP.
Yeah, that would mean there's some structural complexity.
No.
Well,
It will be some issues here.
yeah.
Why?
There are some
So maybe that, so what kind of reduction when you say co-NP hard? What kind of reduction you use?
It's not going to be that, as I know.
It's coin P hard. Why?
Could you please just show that slide? Maybe
Okay.
maybe it's just written over there.
But what kind of reduction? If it's just
So for
polynomial function,
Oh, wait.
reduction.
Excuse me.
Yeah. So yeah.
It's not going to be hard.
I think you didn't just mean that going to be hard.
No, it's hard with respect to Turing reduction, of course,
Well,
but this doesn't mean anything.
And I'm.
It's not going to be hard.
It's coin P hard. Okay, let's discuss it later.
maybe we should discuss it
Yes,
offline, but
I'm not
this
so
is kind
big,
of strange.
so big specialist in complexity theory actually.
In many cases, it has nothing to do with the malicious result.
Yes, that's not mine, but
Right.
it follows from.
Any other questions? So, if not, let's thank Misha and all the speakers.